Hi everyone. Through this class, we are going to study about the construction and working of semiconductor laser. A semiconductor diode laser is a specially fabricated PN junction device which emits coherent light when it is forward biased. Robert N. Hall and his co-workers made the first semiconductor laser in 1962. It is made from gallium arsenide, which operated at low temperatures and emitted light in near infrared region. Semiconductor lasers working at room temperature and in continuous wave mode are produced by 1970. Now, PN junction lasers are made to emit light almost anywhere in the spectrum from UV to IR. Semiconductor is a material with electrical properties lying in between that of conductors and insulators. A range of energy possessed by valence electrons is called valence band, and a range of energy possessed by conduction electrons or free electrons is called conduction band. The energy gap between conduction band and valence band is called band gap. Energy gap is small in semiconductor. Population inversion is required for producing stimulated emission. The way in which population inversion is achieved in semiconductors is very different from the way it is established in other types of lasers. A semiconductor cannot be regarded as a two-level atomic system. It consists of electrons and holes distributed in the respective energy bands. Therefore, laser action in semiconductors involves energy bands rather than discrete levels. In semiconductors, electrons are not associated with specific atoms but are injected into the conduction band from the external circuit. Therefore, conduction band plays the role of excited level while the valence band plays the role of ground level. Population inversion requires the presence of large concentration of electrons in the conduction band and a large concentration of vacancies or holes in the valence band. A simple way to achieve population inversion is to use a semiconductor in the form of PN junction diode formed by heavily doped P and N type semiconductors. A diode laser consists of heavily doped PN junction. A simple diode makes use of the same semiconductor material, say gallium arsenide. Starting with a heavily doped N-type gallium arsenide material, a P region is formed above this by diffusing trivalent zinc atoms into it. A heavily zinc-doped layer constitutes the heavily doped P region above this N region. The diode is extremely small in size. Typical diode chips are 500 micrometer length, 100 micrometer wide and 100 micrometer thick. The top and bottom faces are metallized and metal contacts are taken from these two metal sides in order to pass the current through the diode. The front and the rear faces, they are polished in order to get the Fabry-Perot resonator out of this. In practice, there is no necessity to polish these faces. A pair of parallel planes cleaved at two ends of the PN junction provides the required reflection from the cavity. Then we have two other sides, this side and the opposite side. They are roughened in order to eliminate the laser flow out of these two faces. The entire structure is packaged in a small case. the energy band diagram of heavily doped PN junction diode is like this. Here at one side we have N-type material, other side we have P-type material, and in between there is PN junction. And in this N-type material, this is the conduction band and this is the valence band. And we can see that in N-type heavily doped material, the free electrons occupy up to a level that we mark it as EF, that is Fermi level. And this Fermi level is above the bottom of the conduction band. Bottom of the conduction band is marked as EC. And the top of the valence band, that is marked as EV. But in this p-type material, the Fermi level is below the top of the valence band. Top of the valence band is EV. So it is below this EV in p-type material. And at thermal equilibrium, we can see that this EF in N-type and EF in p-type, they are on same line. When the diode is forward biased, electrons in this N-type material, they get sufficient energy and they jump to conduction band. So the Fermi level in this conduction band, it rises. And during the forward biasing, here the number of free holes, these holes increases. Holes means vacancy of electron, that increases. That means Fermi level in this p-type material, that falls. So during forward biasing, Fermi level in N-type rises and Fermi level in this p-type falls. And this high number of free electrons, they will inject these free electrons into this junction. And here there will be large amount of holes. They are also injected into this region. So here we can see that a number of free electrons in this conduction band and there are number of holes in this valence band. Holes means vacancy of electrons. So the above level, that is conduction band, it acts like the high energy level, and here the absence of free electrons or presence of holes in this valence band, that represent the ground energy level. So this region where we get the population inversion, here more number of free electrons in conduction band, it represent a state of population inversion here. And this region we call it as active layer or active region. And the narrow zone in which there is population inversion occurs is called as inversion region, or we call it as active region. The chance of recombination of free electrons and these holes led to a spontaneous photon. The spontaneously emitted photon propagates in the junction and it moves towards the plane, stimulate the conduction electron to jump into the vacant states of valence bands. The stimulated electron-hole recombination produces a coherent radiation. Gallium arsenide laser emits light of wavelength 9000 angstrom unit in IR region. There are many advantages for this diode laser. Its efficiency is very large compared to other lasers, up to 40% efficiency possible for this. And the power output is very high, and for its operation it needs very low power. And one main advantage of this diode laser is it is portable and the size is very small, and the cost compared to other lasers, it is very low. Diode lasers are widely used in optical fiber communication. They are used in CD players and in optical reading and in high-speed laser printing.